Nuclear force. The average separation between two nucleons. The average separation between two nucleons is about 10 raised to minus 15 meter. 10 raised to minus 15 meter. At this separation, positively charged protons have strong Coulombic repulsion between each other. Also, the gravitational force of attraction, also the gravitational force of attraction between two nucleons is about 10 raised to minus 36 times smaller than that of the electrostatic repulsion. So, this gravitational force cannot hold the nucleons together. So, there must be some other strong attractive force acting between the nucleons that overcomes the electrostatic repulsion. This strong attractive interaction acting between the nucleons is called nuclear force. So, nuclear force is a strong attractive force that binds the protons and neutrons together inside a tiny nucleus. Properties of nuclear force. Strongest interaction. Nuclear force is the strongest force in nature that hold the nucleons together. Then second point, nuclear force is a short range force. That is, it operates only up to a very short distance of about 2 to 3 Fermi meter from a nucleon. Fermi meter means 10 raised to minus 15 meter. Then third property, it is a charge independent character. That is, the attractive force between two neutrons is nearly equal to that between two proton or between a proton and a neutron. Thus, the nuclear force does not depend on the charge of the particle because it is the force of attraction between two proton or a proton and a neutron. So, it does not depend on the charge of the particles. So, it is a charge independent. It has a charge independent character. The fourth point is variation with the distance. That is, nuclear force varies with the distance. The graph shows the potential energy of a pair of nucleons and the distance between the nucleons, that is denoted as R, and its range is in the order of Fermi meter, that is 10 raised to minus 15 meter. So, if the distance between the nucleons is 0.8 Fermi meter, that is center to center, distance between the nucleons is 0.8 Fermi meter, then this value. So, it has that is the pair of nucleons has minimum potential energy. So, the nuclear force is attractive in nature. It has the maximum attraction. At this value 0.8 Fermi meter, potential energy is minimum and the nuclear force is attractive in nature. It has the maximum attraction. Then the distance between the nucleons are less than this value 0.8 Fermi meter, that is R0. Distance between the nucleons is less than 0.8 Fermi meter, then they repel each other. They repel each other. So, its potential energy increases. When they repel each other, it attains a maximum distance. So, its potential energy increases. Then we can write the potential energy R less than R0. Potential energy increases rapidly. Okay, potential energy increases rapidly and the force is repulsive in nature, repulsive force. Force is repulsive in nature. So, we can note here that is the repulsive force. Potential energy increases and force is repulsive in nature. Then, in the second case, if this distance between the nucleons are greater than R0, okay, distance between the nucleons are greater than R0, then what happens here? Then the potential energy, that is R is greater than R0, then they shows a attractive in nature. Okay, when the potential energy, when the distance between the nucleons are greater than this 0.8 Fermi meter, then it shows a attractive in nature. But the potential energy is negative. Okay, potential energy is negative. So we can write when R greater than R0, potential energy gradually decreases and the force is attractive. So when the distance between the nucleons beyond 2 Fermi meter, the potential energy decreases and it becomes 0. So the nuclear force also becomes 0. That means there should be no force of attraction or repulsion between the nucleons when the distance between the nucleons is beyond 2 Fermi meter. This represents that the nuclear force is a short range force. So, at 0.8 Fermi meter, the distance between the nucleons is 0.8 Fermi meter. The potential energy is minimum. Okay, the potential energy is minimum and it has a greater attractivity. That is, attraction is maximum. Attraction between the nucleons is maximum. Attraction is maximum. Then R less than R0, then the potential energy increases. It shows the repulsive nature of nuclear force. When R greater than R0, potential energy gradually decreases and it is a negative value, but the nuclear force shows attractive in nature. Beyond 2 Fermi meter, the potential energy gradually decreases to 0. So the nuclear force becomes 0. There is no force of attraction or repulsion between beyond 2 Fermi meter. Okay. So the nuclear force is a short range force. So the negative sign in the potential energy represents that nuclear force is attractive. Mass energy equivalence. Einstein, in his special theory of relativity, says that mass is also a form of energy. So he called this energy as mass energy. That is, energy associated with mass. Mass energy can be converted into other forms of energy. For example, when we switch on the bulb, electrical energy is converted into light energy. So, mass energy can be converted into other forms. That is, how much energy is associated with the mass m, that is the mass energy. So, according to Einstein, this can be written as E equal to mc square, where mc square is the mass energy. Any object which has mass m, it has got an energy associated with mass m. That energy is because of its kinetic or because of its motion or because of its position, which means that this object has mass m. So, anything that has mass energy associated with it, that is E equal to mc square. So, this equation also suggests that even when a particle is at rest, it still possesses an enormous amount of energy because of its mass. Mass defect. What do you mean by this mass defect? Mass of a stable nucleus is always less than the sum of the masses of its constituent protons and neutrons in their free state. Let us see with one example. Consider the oxygen nucleus, that is O16 8, having 8 neutrons and 8 protons. So first we have to calculate the mass of oxygen nucleus by adding the masses of protons and neutrons. So the mass of 8 neutrons equal to 8 into 1.00866 atomic mass unit, and mass of 8 protons 8 into 1.00727 atomic mass unit, and mass of 8 electrons 8 into 0.00055 atomic mass unit. So we can calculate the mass of oxygen nucleus by adding the mass of 8 neutrons and 8 protons. So we get the value 16.12744 unit. Then also we can calculate the mass of oxygen nucleus from experiment. So from mass spectroscopy experiment, atomic mass of oxygen is 15.99493 atomic mass unit. This mass contains mass of 8 neutrons, 8 protons and 8 electrons. When you subtract the mass of 8 electrons from this atomic mass, we get the experimental mass of oxygen nucleus, that is equal to 15.99053 atomic mass unit. So, the difference between this experimental value and this expected mass of oxygen nucleus, that is mass of 8 protons and 8 neutrons, is 0.13691 unit. So this is the difference in mass between the mass of oxygen nucleus and mass of sum of the constituents of protons and neutrons. This difference in mass is known as the mass defect. It is calculated using the formula delta M, mass defect delta M equal to ZMB plus A minus ZMN, that is sum of the masses of protons and neutrons minus the experimental mass of nucleus, that is capital M. So we can define the mass defect as the difference between the rest mass of a nucleus and the sum of the rest masses of its constituent nucleus. Once again, the difference between rest mass of a nucleus and the sum of the rest masses of its constituent nucleus is called its mass defect.